All right, functional groups. So far we've talked about alkanes, right? Alkanes are also known as what?
Saturated hydrocarbons.
Alkanes are saturated hydrocarbons. And then yesterday we talked about alkenes and alkynes, right? Alkenes have double bonds, alkynes have triple bonds, and those are unsaturated. So we have categories of organic compounds that are based not so much on. Hang on 1 second. My Apple Pencil is not working. I have to switch. There are compounds that are based on what is attached to them, like what is attached to the carbon chain. And so that's what we mean by functional groups. Some of these should be familiar because we have alluded to them or seen them or used them directly, like alcohols. So an alcohol is when you have a functional group of OH attached to the carbon chain. Now, I'm going to be using this R. R means generic carbon chain. Okay, it could be like 1 carbon long, it could be like 10 carbons long. It doesn't matter. That's not the point. The point is just the functional group is attached to some number of carbons. Okay, it's like a stand-in. Okay, now the OH group has a name. This is called the hydroxyl, which kind of makes sense because you've seen the OH minus ion is hydroxide, right? So hydrogen, oxygen, hydrox, right? That makes sense. So that's the hydroxyl group. So whenever you have OH attached, so methanol would be drawn this way, right? So how do you name it? Well, you find how many carbons there are, you use that prefix, and you end it with "all," the suffix, right? So instead of methane, it's methanol. This 2 carbons, instead of ethane, it would be ethanol, and so on. So what would this be called? Butanol, right? Okay. Now, I'm going to add a page because to go into a little more depth here. Sorry, I'm going to jump down here to some blank space because I want to show you some other things that were not in there. So there's different classifications of alcohols. You have what are called primary alcohols, and those are when the OH is attached to a carbon that is attached to one other carbon. If that makes sense. So, for example, in other words, the OH is attached to a terminal carbon. Remember what terminal means? On an end, right. So, CCCOH, that's a primary alcohol because the carbon that it's attached to right here, how many carbons is that carbon attached to? Only 1. That's a primary alcohol. And it doesn't matter how long the carbon chain is, right? It's just the point is the carbon is only attached to one other carbon. Or a primary alcohol is one that's where the OH is attached to the end. Then we have what's called a secondary alcohol. And that's when the OH is attached to a carbon that is attached to 2 carbons. Or in other words, the OH is a branch. Okay, so something like this. All right, the hydroxyl is attached to that middle carbon there, and that middle carbon is attached to two other carbons. That makes this a secondary alcohol. All right, and so because it's a branch, you need to involve carbon number in your naming conventions. So call this 1, call this 2, call this 3. This would be 2-propanol. Because there's 3 carbons long, it's an alcohol, and the functional group is on carbon 2. That makes sense? Okay. Should the unlikely event arise where you have an alcohol as a branch and you have another, like a methyl or ethyl or propyl branch attached, you would give priority to the functional group for the lower carbon number. Okay. Then we have what's called a tertiary alcohol, and that's when the OH is attached to a carbon that is attached to 3 carbons. This is not as common, but it would look something like this. The carbon that holds on to the functional group is bonded to 3 other carbons. Yeah?
Like if, like say for example, they asked us to like draw the primary, like would they tell us like, oh, draw a primary alcohol or secondary alcohol diagram? Because how do we know?
They probably likely would not tell you to draw a primary, secondary, tertiary. More so, they would give you the name, and you would have to deduce from the name where the OH is attached to. Okay. Yeah. So if I said, let's pick a different color here. Let's draw 3-methyl 2-hexanol. So remember, I always start with parent chain. Parent chain is going to be 6 carbons. And the functional group for the alcohol is on carbon 2, and on carbon 3 we have a methyl group. So this is a secondary alcohol, but they didn't bring up the word secondary alcohol. You just drew it based on the name. Yes?
Like, would it be 2 hex, or you said like functional group has the priority in terms of naming, so would it be like 2-hexanol, 3-methyl, but that doesn't make sense?
No, what I meant was the functional group has the priority for the lower numbered carbon conventions. Yeah. The branches still come before the parent chain name. Okay. One thing to note about alcohols. Okay, so back in Unit 3, you learned that when we have a compound with OH, it's a base. You remember that? So actually, here, let's go back to where there's room. They're not bases. Okay? Any alcohol, any formula, CH3, CH2, CH2, OH, they have the OH on them, but you have to understand the fundamental difference between this and a base. The bases, we're talking about ions, ionic bonding, right? So something like this, KOH, that's a base, and primarily because it's the fact that it can ionize. It's ionic, right? These, all the bonds here are covalent bonds, and covalent bonds do not ionize, at least not nearly as much. They don't ionize. There's no release of OH minus, hence not a base. Just gonna get out there and say it right now, okay? Okay. So that's That's alcohols. Alcohols can be prepared by fermentation, right? You might have talked about that in biology, right? And as far as you might have heard the term proof, proof is 2 times the percentage of whatever the alcohol is. So if something was like 50% alcohol, we would call that 100 proof. Although I'm not sure why I'm bringing that up. It seems mildly inappropriate, but it's here now, I guess. Okay, let's move on to our second group called the carboxyl group. So a carboxyl group looks like this. You have a carbon that is double bonded to an oxygen, but also has a hydroxyl group. Okay, and then it's attached to some number of carbons, right? 1, 2, 3, 4. R actually can be an H as well. So we can, if that was just an H, then that would be the entire length of the molecule. So carboxyl groups are responsible for something to become an acid. This is where your organic acids come from. So they come from carboxyl groups. So the reason why this is an acid is because in a carboxyl group, you have these oxygens, this oxygen right here, and this oxygen here. You have 2 oxygens close to each other. And what they do is the bond that's right here, this little green bond, this covalent bond is weakened because the electron density is drawn towards the more electronegative oxygens, plural. Okay, so what that means is the dipole moment in this direction is strong. Right? In this direction is strong. So the electrons that are involved in the bond right here between O and H, they're being pulled towards oxygen so much that the hydrogen, it doesn't take much for someone to come along and just kind of pluck it off. Right? And so what that would mean is then you have this, and the H is most likely attracted to, because we're dealing primarily in solution, it's most likely attracted to a water molecule, resulting in H3O+, which we know as hydronium. Okay, so this is an important concept in bonding and as far as acids. All right, we're going to talk, we have an official unit on acids later, and we'll talk about this again in more in depth. But basically, I'm just showing this now to you so you understand why it is that this carboxyl group is an acid. It's because this guy here gets dissociated. All right, so acetic acid, lauric acid, any one of those organic acids, propanoic acid, ethanoic acid, they are acids because they can produce H+ in solution. Now, are they strong acids? Well, are they on the list of strong acids? No, they are not. So you know these are weak acids, okay? Okay. So, how do we name an acid when we see one? You just drop the E from the alkane name, and then you add oic acid. Right, so however many carbons long it is, something like this, 5 carbons long. If this was an alkane, we'd call it pentane, but you drop the E, and now it's pentanoic acid, and that's how we would name that. Rowan?
Will the carboxyl group always be usually terminal?
Yes. Yeah, with acids, because of the fact that your carbon cannot be, because of its structure, it cannot be somewhere in the middle of the chain. It's got to be terminal.
So if there was like a methyl group saying carbon 3, it would just be 3-methyl pentanoic acid.
Yes.
Okay.
Okay. Treatment with a base produces a salt. Huh. So you're telling me if I take an acid and react it with a base, I get a salt? This is something you already knew, right? You know neutralization is when an acid reacts with a base. You get water and a salt. So acetic acid plus sodium hydroxide, you get water and sodium acetate. Okay. All right. So since we're talking about acids, fatty acids are long chain acids. Okay, so when a chain gets long, come to think of it, sorry, I'm going to take an aside here. I'm going to go to my extra page I added. This question came up and we didn't really address it earlier. Okay, but with an alkane, so remember how we talked about there's all different ways to write organic formulas? There's the conventional formula, which is something like this, C5H12, right? And then we said that there was the structural formula, which essentially is a Lewis diagram, right? And then we said there's condensed structural, which is this, which shows all of the elements, all of the atoms for the elements, but in order, progressing from left to right. This is another way. And the other way is what we call a line structure. A line structure is when carbons are assumed to be at vertices. So watch. That is pentane. Except that typically they don't bother writing the C's. So this would just be drawn like that. Organic chemists look at that and say, oh, that's pentane. How did I know it's pentane? There's 5 vertices, right? 1, 2, 3, 4, 5. So line structures are very efficient ways, very, very efficient ways of drawing simple organic molecules. Okay, so be prepared to see these and know what is being shown. So if I gave you another line structure like this, and I said, what is that? You would follow the same convention that you've been doing, right? Find the parent chain. How long is the parent chain there? 4 carbons. And what's that thing sticking off to the side? A branch, and that branch means one more carbon. So that one carbon branch is what? A methyl. So what's the name? 2-methylbutane, right. Okay. And the reason why I'm bringing this up, how to interpret line structures, because you need to know it, but also, if we talk about something like fats, we go back up to our acids section. Long chain fatty acids. By long chain, we mean like long. Like more beyond the prefixes that we learned. Okay? And so we get these guys here. That's a fat. Right? And depending on how long they are, it could the dispersion forces could build up, and your fat could turn into a liquid, or it's going to be liquid, but you can turn into a solid. Right? So, okay. So acids. Have the carboxylic group at the end. All right, next category. Esters. Esters are formed by the reaction of an acid with an alcohol. Oh, now you know what a carboxylic acid is, and now you know what an alcohol is. So when these combine, we get what's called an ester. An ester is a molecule that's most associated with smells, perfumes, fruity smells. So here's what happens. you see how this guy right here, right? So that's condensed structural for an acid. That's actually ethanoic acid, right? So the structure of this is actually this. I'm gonna make the H a different color. Does that diagram make sense? So when you have a C followed by two O's, the only way that those O's can both be bonded to the carbon is if one of them is double bonded and the other one is singly bonded. You can't have two O's double bonded carbon if that carbon is also bonded to carbon. That would be 5 bonds, which is not possible. Okay, so that's the structural formula. And then we have the structural formula for ethanol, but I'm going to write the ethanol, I'm going to write the direction backwards. All right, that's ethanol. 2 carbons and a hydroxyl group. So what happens is when you react the acid with the alcohol, what do acids do? They give off H+, right? What's going to happen here is that the hydroxyl group of the alcohol breaks off and binds to the hydrogen, the result of which is this. Water. And then, when the other part, the acid component, right here, oh, that's big. That part is right here. And the remainder of the alcohol is this. So we have a new bond formed right here that joins the alcohol component with the acid component. And this, collectively, this new molecule is called an ester. This is an important reaction. You need to understand that when you have an organic acid and you have an alcohol, when they combine, this is another category of reaction called dehydration synthesis, because you're pulling out water to synthesize a new formula, a new molecule. Okay, but it's always, and if you ever forget what part comes off what, just remember acids donate the H+. If you're forming water and you got H+ from the acid, then what must you take from the alcohol? It must be the remains, the OH. Okay? Yeah?
So in this bond with the H on the right end of the alcohol bond with the oxygen on the right side of the acid? Or the
It's not the H, it's actually the whole OH. So if I were to color, let me find another color. We'll make this guy here the functional group purple, which is this. So that part was from the alcohol. The H was from the acid. Sorry, there's so many colors going on here right now. And this is going to take practice. So let's do some more practice with this. Let's find some space. I kind of have some space here. Okay, so let's say we have this. Okay, so this is what we call methanoic acid. Everyone see that? Methanoic acid? Because it's 1 carbon and it's got the carboxylic acid group. If I react this with propanol, It's the H plus from the acid. It's the OH from the alcohol, the hydroxyl. We're going to get this. I should have used a different color. I'll switch colors now. Is that clear? The ester, what part comes from which part? Okay. So that's our ester. And we got to name esters, right? Although Esther is a beautiful name, right? It reminds you of your grandma, probably, right? But it's not all esters are named the same. So to name it, you take the root of the alcohol, and then you take the number of carbons in the acid, and you add O8 to it. So this is going to be propyl, right? Because the 3 carbons from the alcohol. And the acid had 1 carbon, so it's methan, but the suffix now changes to O8. Propyl methanoate. So this is from the alcohol. This part's from the acid. And then make sure you use the right suffix. So the esters are very important industrially. If you become a chemical engineer, you might spend a lot of time, depending on what company you work for, developing, stabilizing esters, because in the food industry, any kind of flavoring requires esters, right? These are your esters are the cause of many scents, and scents are the backbone of flavors. So something as simple as a Jolly Rancher's cherry candy, right? Or a Mountain Dew, or, any kind of food product you're developing, you're going to have some kind of flavoring added to it, like granted, if you're doing this in a lab, this is an artificial flavor, but these are actually made in nature as well. That's why you can have extracts. What are they extracting when they extract vanilla? They're extracting an ester from the natural vanilla essence, right? So this is where flavors come from, or at least many of them. Okay, so a fat is a long chain acid with a glycerol molecule. This guy here, this is called glycerol, right? So if you look, essentially what glycerol is, it's got 3 hydroxides, right? It's like a trialcohol. And how could you form a fat from this? Well, if they're all alcohols, that means they can react with acids in esterification processes, right? It means this guy, and this guy could pop off and be attached to an acid after the acid dissociates its H+. So that means right here, here, and here, that's these guys. And so that's where you traditionally get a fat from. All right. Just a couple more to go. We'll have 3 more to cover. There are more than 3, but these are the most fundamental, the most basic ones we must cover. Oh, actually, strike that. Need to go over another important aspect. Add another page. since we're on the topic of fats, there are what we call saturated or unsaturated fats. You might have heard this term before, right? If you read the labeling, the advertising labeling on a package, right, for health conscious products. So, okay, you know something about these terms already. You know that if it's saturated, that means that there's the maximum number of hydrogens that are bonded. Okay, so if you have a fat where everything is just hydrogens, saturated fats have lots of dispersion forces because fats are primarily nonpolar. Even though they have polar ends, the vast majority of a fat molecule is nonpolar because it's an alkane. So there's lots of dispersion forces and there's lots of surface area. So what happens when you have lots of surface area and your primary intermolecular attraction is dispersion forces? They all cling together pretty well. And so saturated fats are solids at room temperature. Okay. But what's an oil? An oil is a liquid fat. How come we have fats that are in liquid and solid form? What must be the difference? So how many dispersion forces there are? So an unsaturated fat, which you should know, has multiple bonds. I'm not going to say double because it could be triple. It has multiple bonds. Okay? And if it has multiple bonds, do you remember we brought up cis-trans isomerism? When you have a double bond and that double bond can cause the carbon chain to kink in a certain direction, right? So we know this as, is it cis or trans? This is cis 3, that's 1, 2, 3, 4, 5, 6. This is 3 hexene, right? And then there was this guy, trans 3 hexene. Okay, so unsaturated fats. When you get these double bonds which have these fixed positions, remember that when the double bonds are fixed in place, there's no rotation, fixed angles. What that eventually leads to is that there's less contact area for dispersion forces. So, if there's less contact, less surface area for dispersion forces, you don't have as many dispersion forces that are effective. You don't have as many intermolecular attractions. So instead of a solid, these are liquids. Because they're not able to make as many effective dispersion forces as a saturated fat. And that's why they're oils. And that's why unsaturated fats are better for you, because they won't solidify as easily, which means they don't get stuck in your arteries as easily, right? So a lot of red meat, which is high in saturated fats, like beef particularly, right? Your body temperature is 98.6 degrees Fahrenheit, but even still, in the extremes, there's going to be places where your body temperature, is not able to keep the fats in liquid form all the time, and especially when they get saturated into your blood as they move through all these pipes, they get snagged and they start to build up. Right? You ever seen the inside of a pipe in your home? Like maybe your parents are remodeling and the plumbers cut through a pipe, and when they cut through a pipe, you can see like the diameter was originally this wide, but then there's like calcification that like takes away a good half of that total diameter, right? So the similar thing happens in your arteries. Okay. Cis and trans. So fats are saturated or unsaturated, and specifically, it should be mentioned that between these two, trans will stack better than cis, meaning trans is more likely to solidify. Even though I said they're both liquids, the trans fats are more likely to solidify than the cis. The cis most likely will never solidify. Olive oils, right? Cis fats. Those are actually good for you because they provide the benefits of the fats without too many of the negative sides of the fats. They don't accumulate and stay in your system as solids. Okay. You know what? This is actually a good place to stop right here for today because I do want us to go over the tests. So we'll cover the rest of the functional groups next